Hello everyone, today we're going to be talking about imaginary numbers. Now before we get into this, there are two topics that you should know in algebra before trying to learn imaginary numbers. Those two topics are the quadratic, and this can be the quadratic equation, the formula to find the solutions for the quadratic equation, and also rules of roots. When I say this is how exponents work when they're multiplied by each other, how square roots work when they're multiplied by each other, because those are essential to what makes an imaginary number. So what is an imaginary number? In the most basic terms, an imaginary number, you can imagine we have a real number line here. Let's write it out like this. So we got all the negative values and all the positive values from negative infinity to infinity, and those are the numbers that we typically work in: -1, -5, 2, 7. When it comes to imaginary numbers, this is a number that cannot be expressed with our basic number line that we would use with negative and positive values, and that comes from the fact of we're going to use the variable I to represent our imaginary number. I is equal to the square root of -1. Now, if you've had practice with square roots, you'll realize that no number multiplied by itself will equal a negative number. And because of that, there isn't a real number or a number that would fall on our number line that would solve this. So instead, we would say that the square root of -1 is equal to I. And we use that fact with any other square roots of negative numbers to just describe it in terms of I. So that's all that imaginary numbers are. They're just a number we can't represent on our basic number line. So we're going to redefine numbers in another form of I, which is a square root of -1. So some examples. Let's see. What's an example of an imaginary number? So we could have I, which is square root of -1, sure. We can say that's equal to I. We can also say something like 2I, which would be 2 times the square root of -1, or 3I, which is 3 times the square root of -1, or even something like pi I. The idea here is that you have a real number multiplied by an imaginary number, and that still makes it an imaginary number. Now, complex numbers are a little different, and we'll see that in this video, and that's something like a real number with an operation like addition or subtraction to an imaginary number. So like 3 plus I, for example. So that would be an example of a complex number. Today we'll focus on imaginary numbers, but complex numbers have a tendency just to show up while you're doing the work. So let's look at an intuitive reasoning of what an imaginary number is. So one of the reasons I said to have practice with quadratics before trying to learn imaginary numbers is this idea here. So when it comes to a quadratic, we're used to seeing something like this, right? We'll see that standard U shape and that it passes through the x-axis here, and that would be our solutions. We find when we find an x to plug into the f of x equation, which is just the quadratic function, and we'll get something that equals 0. So at what x value does the y value equal 0? And that's when the line passes through the x-intercept. And that's what we're used to. We're used to solving for that, whether it's just the factorization method or the quadratic equation to find two values we should be getting for that. Unless it meets at the origin or just touches the x-intercept, then you'll just get one value. But the point does stand where we're used to this, where we're solving for two values. Now when it comes to an imaginary number, the way to visualize this is, say we have another quadratic equation, same idea, but it looks something like this. So you still got the U shape, it still follows all the standard conventions of a quadratic equation. However, it does not touch the x-intercept. And you can see that clearly here. You can see that there's this distance between it at all times. It just never touches it. No matter where you go from all your x values, it does not get close enough to the line to touch it. It does not pass through the line. And what you can imagine when we talked about our number line, we talked about how when our number line goes from negative infinity to infinity, those are our real numbers. When we plug in any real number into the x value, we'll never get a y value that equals 0. That's just a way of saying there's not a solution for it. Same way as there's not a solution for the square root of -1. So with that in mind, let's just look at an example of when this might show up when working with quadratics. And this is why it's so important to have that exposure in quadratics, because that's most likely the first time you will see an imaginary number or be introduced to the topic of what a square root of a negative number actually is. So now let's say we have the quadratic equation y equals x squared plus 2x plus 3. So we're going to plot this over on the right here of what that's going to look like. And it's going to be something to the tune of this. Again, it might not be perfect, but the point of looking at this is that it does not touch the x-intercept. So just by drawing it on a chart, we know there's not a solution. But we know we can look at the factoring method if we wanted to, which make an x here. You got 3 on the top, 1 times 3, and 2 on the bottom. Okay, what can we multiply two numbers to get 3 and add up to 2? Take a second to look at. You can't just do any basic like that. So then we would resort to our quadratic equation to find a more complex number that maybe fits but isn't a perfect whole number. So our quadratic equation is x equals negative b plus or minus square root, and that's b squared minus 4ac all over 2a. Okay, so maybe if we plug in here, we'll find a solution, right? So we'll do that. Negative b, that's negative 2, plus or minus square root of 2 squared, which is 4, minus 4 times a, which is 1, times c, which is 3, all over 2a, is just 1. And this simplifies the negative 2 plus or minus square root. And this is going to be 4 minus 12 all over 2. And let's do another final simplification of this. So it's going to be negative 2 plus or minus square root of negative 8 all divided by 2. And if you've been following along, you'll see this is where the problem arises. So normally you would just solve the negative and the positive and get your two answers for the equation, call it a day, everything's happy, it works out. When you look at this, the key difference in an equation that doesn't touch the x-axis is that you're going to have this section of the equation right here. You're going to have the square root. You're going to see there's a negative number in the square root. What that means is there's no real number that we can get as a solution. So from negative infinity to infinity on our normal or regular real number timeline, there's not going to be a number that works. We can't solve for a negative square root of something. So rather, we're going to describe this in terms of an imaginary number. So it's negative 2 on the top still, plus or minus. And then what can we say that negative square root of 8 is? And that's kind of where we're going to redefine this equation a little bit. Okay, well, let's work over here quick and kind of look at that. We can write out the square root of negative 8 and separate this into the square root of negative 1 times the square root of 8. The idea here is that we're separating the imaginary part, square root of negative 1, and the real number part, the square root of 8. And you can multiply that together just with the rules of how square roots work. So we've already defined that the square root of negative 1 is called I. And we can further separate the square root of 8 here into two parts. Square root of 4 times the square root of 2. We know that square root of 4 is just 2, so this can be expressed as 2 square roots of 2. And we still have this I part right here. So we can express that the square root of negative 8 is equal to I times 2 square roots of 2. So you can say I times 2 square roots of 2 or 2 square roots of 2I. That might be preferable. But we'll just write it this way for now, just to keep it kind of simple. Okay, so now we know what the square root of negative 8 is. So we can fulfill that section with what we just got. I times 2 square roots of 2. And we know this is all over 2. And then we can further simplify this. We know that negative 2 we can divide by 2, the denominator here, which would be negative 1. And then plus or minus. And we know that this is 2 square root of 2 times I. And we can divide that all by 2 since it's connected with multiplication. So we can say this is square roots of 2I, or I times square root of 2. So this means that the answers for our quadratic equation would be -1 plus or minus square root of 2I, or I times the square root of 2. And that comes with the idea that there's not any real solutions going from -infinity to infinity on our normal real number timeline. So we're going to rather use an imaginary solution to represent that. Now, when you're learning about imaginary numbers, another important idea is operations. So how do operations with I work? Okay, well, before that, let's talk about a little bit of a pattern that we might see. Okay, so we know that I is equal to the square root of -1. That's what we've defined it as. So we're going to write out some exponents of I. Okay, so say we just write the ascending exponents. We know that I is equal to square root of -1, which we can just say that's I. I squared would be square root of -1 squared, which when you square a square root, it undoes itself, so we're just going to have -1 here. Okay, and now for I cubed, we're going to have square root of -1 cubed, and this comes out to be -1 times square root of -1, which is -I, and then we're going to have -1 to the 4th, which is equal to, well, you can say it's -1 squared times, square root of -1 squared times the square root of -1 squared, which we've already said earlier would be -1 times -1, which equals 1. And then when it comes to I to the 5th, this can be represented as I to the 4th times I. We said I to the 4th is 1 times I then, and that just comes back to I. So when it comes to working with exponents, you're going to see this pattern which goes from I, -1, I, 1, and then back to I. And this is just going to basically repeat and repeat as you go about it. So it is a little nifty trick when it comes to the exponents, and something that you might encounter in a problem, and I'll show some of those examples. But when it comes to the actual operations of how I interacts, that might be where some confusion comes up. So let's look at some basic operations. Say we have 2 plus 4I, and then that subtracts 1 plus 3I. So I'm just going to write it in terms of parentheses just so you can practice some of that. But you could say 2 plus 4I minus 1 minus 3I, same exact concept. So when you have this and you're working with real numbers and imaginary numbers, just remember to pair it up. Real numbers go with real numbers, imaginary numbers go with imaginary numbers. So let's see what we have here. So we have 2 as a real number, 1 as a real number, 2 minus 1, that's 1. And then we have 4I as an imaginary number, and 3I as an imaginary number. 4I minus 3I is just I. So our total answer is 1 plus I. That would be a complex number, which we talked about earlier. So yeah. And then let's look at another example here. Say we have 4 plus 3I in parentheses, and that's multiplied by parentheses of 1 plus 2I. Okay, so we're going to treat this like normal multiplication of parentheses and just see what comes out and kind of explain from there. And this is why it's important to look at how this pattern works and how I interacts with exponents. So taking this, first we're going to have 4 times 1, which is 4. Then we're going to have 4 times 2I. So you're just going to multiply the two real numbers and then you have the I attached to it. So 4 times 2I would be 4 times 2, which is 8, times I, so 8I. And then say we got 3I times 1, which is going to be plus 3I. Then we got 3I times 2I, which is going to be 3 times 2, which is 6. I times I is I squared. Okay. Well, let's simplify here. We got the real number 4, no other real numbers involved, plus 8i plus 3i. 8i plus 3i is 8 plus 3, which is 11. You have I attached, so 11i. And then we have 6i squared. And this is where it's important to know how exponents interact with I. We already said that I squared. It's the same thing as saying square root of negative 1 squared. Squared undoes a square root. So this is just negative 1. So what we're going to have is 6 times negative 1. So this is 4 plus 11i plus 6 times negative 1, so minus 6. And now we have two real numbers left, so let's just start with 11i here. Then we're going to have 4 minus 6, which is negative 2. So 11i minus 2 would be the solution to that. Okay, moving on from that, let's get into some practice problems here. So these are some problems you might expect to see when you're learning about imaginary numbers, some trick questions you might throw in there just to try to confuse you. So let's say we have square root of negative 13. How can we represent this in terms of an imaginary number? Well, when it comes to this, the key idea is that you want to separate imaginary from real, or those typical numbers we work with. So we know we have to represent this in terms of I, which is square root of negative 1. And that's going to be multiplied by the square root of 13. And that's just the rule of square roots, where you can multiply the inside. And as long as you multiply the square roots, you're going to get the same inside. And you'll get the same answer at the end of it. So we know that this is the same thing as saying square root of negative 1 is I times square root of 13, which we can't simplify any further. So I square roots of 13 will be the answer to that. That's how we could represent it. Or we say it's square root of 13 i's. However you want, it's the same value. Now let's get into a little bit of a longer one here. Say we got 2 plus 4i plus 6 minus 2i plus 3 plus 5i. Okay, so we kind of got a lot of parts working here, but the same idea as before. Let's start with the real numbers and imaginary numbers, separate them, and then see if there's anything further that needs to be done. So we got 2 plus 6 plus 3. Okay, and that's just going to be 11 for real numbers. Okay, and let's highlight the imaginary. For imaginary, we got 4, and then plus negative 2, so minus 2, and then plus 5. And this is the same thing as saying 7. So 11 plus 7i would be how we could describe that. And there's no further way of simplifying I, so this is fine. If it was I squared, we would go further and simplify it. But you only really run into that if you're working with I squares to start with, or if you're multiplying two I values by each other. Okay. Let's say we got 4i, and we're multiplying that by 2i. Okay, well, let's multiply the real numbers first. So 4 and 2, so that's 8. Then I times I. A variable multiplied by itself is that variable squared. So I squared. And we know this is the same thing as saying 8 times square roots of negative 1 squared. And that's the same thing as saying 8 times negative 1, because square root of negative 1 squared, or I squared, is negative 1. So 8 times negative 1 would be negative 8 as our final answer. Let's say we got I times 2i times 4i. So this is where we're going to work in a little bit of higher powers than just I squared. So we're going to have 1 times 2 times 4 for the real numbers. And that's going to be multiplied by I times I times I. Okay, 1 times 2 times 4, that's 8. I times I times I, that's I cubed. And we've already expressed before that I cubed is saying the same thing as, let's double check here, yep, negative I. And we can express that in this way. So say you have 8, which is the real numbers, and you're going to have I squared times I. That might be an easier way of just kind of breaking it down. So 8 times I squared, which is -1. I itself cannot be simplified. So this comes out to -8 I. So sometimes when you're working with multiple i's, multiplying them, you get higher than just the squared exponent, which is easiest to work with. So it's important to understand that cycle that you go through when you're exponentializing the I value, the square root of -1 value. Okay, so let's do another one, which, yeah. So this is a good one of understanding where that pattern can kind of come into play. So say you have I to the 120th power. Okay, that might be a little confusing, understandably. And you might think, well, how can I even start at this? I don't want to have to go through that entire pattern 120 times, and that's completely understandable. And this is where it comes into play that we know I to the 4th is equal to 1. And every I to the 4th, you're going to have 1. And this makes it incredibly easy to work with, because you can say I to the 4th, and then to the power of 30, which is saying I to the 4th times I to the 4th, saying that times 30 times. That's because every time you multiply that, you're going to have the 4 just adding on itself. So we can kind of write that in this different form of I to the 4th to the 30th power, because when you have this form of exponents, these two values are just multiplying each other. So I to the 120th power is the same thing as saying I to the 4th to the 30th power. So a little bit of a trick. It's important to know your exponential rules. This is where it kind of comes into play. Well, we know that I to the 4th is simply 1. And that every single time you get I to the 4th, it's just going to be 1. And that's where this is incredibly helpful, because now with this in mind, you're going to have 1 to the 30th power. Well, when you're multiplying 1 by itself, it's just going to be 1. So the answer to I to the 120th power is just 1. Okay, so that was a simple one. So you can think if it's a multiple of 4 evenly, answer is just going to be 1. But what if it's not a perfect multiple of 4? Say we have I to the 17th. What I would recommend, the fastest way to do this, is split it into 2 parts. The first part is going to be the highest multiple of 4, so 16. 4 times 4 times is 16. And you're going to be left with I to the 1 power, or just I if you want to represent that way. So we already know I to the 16th, because it's a multiple of 4, can be represented as 1, using the same trick as above. Times that by I, because that's what's left over, and your answer is going to be I. So if you use that pattern established before, break into an exponential power that can be represented by 4, so you get 1, and then you'll see what's left over, and it should just be one of those patterns. You should be able to easily solve it, say if it's I to the 3rd, just by applying exponential rules. So let's go over one final problem here, and we'll call it a day at that. 6 plus 2i, and we're going to multiply that by I. So it's a nice one to finish on. When you multiply, you're going to multiply by each parts inside the parentheses. So we have 6 times I, which is 6i, plus 2i times I, which would be 2i squared. So we know 6i can't be simplified any further, but I squared can be, because I squared, well, I is the square root of -1. When you square that, you're just going to get -1. So we got 6i plus 2 times -1. And that's equal to 6i minus 2, which is a complex number. All these rules are the basics that you'll see when working with imaginary numbers. If you're just at that starter level, you really won't need to know anything further. At higher mathematics, I'm sure it gets much more complicated, not even something I've worked with. But nonetheless, practicing these types of problems, especially the ones I showed you at the end here on this page, these are really good example problems of what you'll see. I think a great way of just trying to understand imaginary numbers is understand the concept that a quadratic may not touch the x-axis, so there might not be an answer, and that's represented by the square root of a negative number. The square root of a negative number simply doesn't exist on the real number line, and that's where imaginary numbers come into play, and that's our way of attempting to describe it in the best way that we can. And sometimes you can transition from imaginary numbers or complex numbers back to real numbers, so it all works out in that.